Hi, welcome to section 4.1. So today we're just going to cover some big ideas about defining a derivative. So first of all, we're going to start out by making connections to algebra. And we're going to just remind ourselves, what is slope? So we've covered this before in previous topics, but let's just make sure that we kind of have a basic understanding. So first of all, if we're talking about slope, then of course we're just talking about having some type of relationship, right? So say I have an x and a y axis, and then I have, as of this point, we've only talked about slope on a line, right? So we define that as usually our rise over run. So rise being the vertical change, right? And then the run being the horizontal change. So run here is usually we call it the change in x, and then rise, we call that the change in y. So what it is it's a proportion, right? This is just a rate of change, which is what we're saying. And we can do this on either side, of course, so it doesn't have to be, as long as it's a right angle, right? Um, so what we're doing again is just finding that change in y over the change in x, and this is how we define it in algebra. So what happens if it's a curve, right? So if it's not just this simple rise over run, maybe we have our same x and y quadrant here, and this time on our graph, say we still had the same graph, maybe from, we'll just mark off 2 points here. And this time, though, instead of having a line, we're going to have actually a curve, right? So some kind of curve happen here. And we want to figure out, okay, well, now what's the slope, right? So what we're going to do is we're going to find the slope of the lines that are tangent to this curve, right? And there's going to be infinite number of lines that are tangent to this, and that's why you'll see C, which is at any given point, right? What is the rate of change there? So basically, if we're changing from a linear graph to something with a curve on it, then we're having to switch from algebra to calculus to be able to do this, right? Because we can tell here in this curve that some of those areas are going to be increasing a little bit faster than others, right? So it's going to have to be done differently. So the fundamental part of this is that basically we can get a slope if we can just get close enough to that curve, right? Because if I can zoom in, zoom in, zoom in, so say maybe here's my curve and I've really zoomed in, then I may be able to get some type of rise over run ratio there, right? So here's the idea. What we're going to use is something called a derivative, right? So derivative is just a rate, just like slope. But what it is it's an instantaneous rate. So what we're trying to find is not just, a simple rise over run, but at any given point on that graph, what is the rise over run? Which again, we're dealing with something that is nonlinear. So let's go ahead and draw in a nice little graph, and I'm going to do my best to make this as straight as possible for you guys. So here we go. All right, so what I'm going to model here is the idea of rise over run on a curve. So I'm going to just draw a curve on my graph. And if I use the same idea as a linear slope, right? So rise over run, then I would have my little right triangle here, just like that. So what I'm going to do is define these points. So maybe here, right, I will call this point just x. And then whatever this is going to be x plus however much the difference is. So if you remember when we're talking about slope, we usually use the definition or the slope formula, which is y2 minus y1 over x2 minus x1, and that's how we get that change in y over the change in x. So I know that from x to this point, whatever that is going to be x plus whatever the change in x is. So what I'm saying is that this side of my graph is going to be defined as the change in x. So that side is pretty easy. But what about for my y values, right? So if I go over here and I mark off where those y values are for these points. So maybe I start at, I'll just call this one f of x, right? So at some point on the graph, that's f of x. And then I have a change in y again, but this is dependent on whatever x plus change in x is. So this one is going to actually be f of x plus the change in x. And that's going to define the change in y. So the change in y is going to be the difference of these two, just like with slope formula. So it's going to be f of x plus change in x, right? Because all we're doing is subtracting, just like we would if this were y2 and y1, right? We would just be subtracting y2 minus y1, which we're just saying is going to be called f of x. And we're just going to divide that all by the change in x. So if you see this and you're thinking, oh my goodness, oh, whoops, I went a little bit too far here, so get rid of this. If you're thinking, oh my goodness, that looked very, very, very close to what I've seen as the definition of a derivative, then you're actually correct. The only other part that we're missing to define a derivative is that the derivative exists there. And in order to do that, then we're going to need the limit. So I'm going to kind of erase a little bit here. I'm going to get rid of that because we just need a change in y there. We didn't need the whole shebang. But what I can do again is I'm going to define the derivative, okay? X plus, I don't want you guys to erase that. It's important. So what we call the derivative, it has many different forms. So you can use dy over dx, okay? Or we also say f prime of x. So you see this little mark up here. It's not a 1, it's not an exponent, it's just a little apostrophe. And the derivative is the limit as x approaches 0. Let me go on because I'm going to run out of space there, guys. So let's do this. Okay, let me try again. So the derivative, which again we can define as f prime of x, is how we say that, is the limit as x, or change in x, approaches 0. So again, this is saying that we have a derivative, or because it's continuous, and then we're going to just write what we had for our slope formula. So based off of the diagram we just had, for any value, we would have f plus the change in x minus f of x all over the change in x. So this is what you guys are going to use to define that derivative. So what you'll do is you guys will just plug in this x plus change in x into your function, and then this again is just your function. So from this point on, it's all just a lot of algebra until you get down to the very end where you can substitute in change of x is 0. Um, and then that will be your derivative. But your challenge for this week is to just make connections between slope and your derivative rule. You guys do have a few problems in Cengage, but just let me know if you guys have any questions on those. And I will see you next time. Bye-bye.